Okay, y'all. So we are going over a chapter 10 review in preparation for the final exam. As I announced in Canvas, the final exam will not be cumulative. It will simply cover the content from chapter 9 to chapter 10. So I decided to focus today on chapter 10 since that's the most recent material. And I'm just going to do a couple problems going over hypothesis testing for population proportions as well as population means. Okay, so this should cover the vast majority of what's important from this chapter, hopefully. Just a couple problems. I will make sure to go over everything as thoroughly as I can. Some people ask about formula sheets for the final exam. I don't see any problem with that. I'm still figuring out the format of the final exam, whether it will be a proctored paper test or potentially just another online test. However, if it is an online test, it will still be scheduled for a certain time at a certain day, and it will be a timed test. So it will not be like the test of previous tests where we got numerous attempts with no time limits or whatever. So all that information will be forthcoming. But for the time being, I wanted to do some review. So let's jump right in. So I'm looking at problems from the back of chapter 10 in the chapter 10 review section. There's a review exercises, and I'm just going to do a couple of these exercises. The first one is number 9. So in number 9, we're told that a proportion of individuals who cover the proportion of individuals who cover their mouth when sneezing is 0.733. Then we're told that out of 100 randomly selected individuals, 78 covered their mouth when sneezing. Okay, so if we were to do a hypothesis test for this, we would need to be able to identify what would be our null hypothesis and our alternate hypothesis. Okay, so without any other info, we're just going to assume that this would be a two-tailed test. We are obviously testing proportion, and the proposed population proportion is 0.733. So if we were to identify the null hypothesis, it would simply be that P is equal to 0.733. The alternate hypothesis would then be P is not equal to 0.733. And we're going to assume it's a two-tailed test since there's not much other information provided. And as we'll see, the claim will be simply that the population proportion, proposed population proportion is not right, is wrong. Okay. Now in part B, if we want to be able to perform a hypothesis test, then we need to know that our sample proportion is behaving like a normal random variable. So is P hat normally distributed? Well, the main criteria here is that we need N times P times 1 minus P to be greater than or equal to 10. So is this true? Well, our N is 100, our P is 0.733, and then 1 minus 0.733. So let's see what that equals. (100) times 0.733 times 1 minus 0.733 gives us 19.57. So this is roughly equal to 20, which is definitely greater than or equal to 10. So that's a check. So now we know that p hat is approximately normally distributed. So that means we can perform a z-test on this sucker. So first, what we need to know is what sort of claim are we testing for? So the claim is, or the question is the population proportion wrong? Is it wrong? So if we're asking, is it wrong, then the claim is that p hat is, or p is not equal to 0.733. So that will be our claim. Great. So now we want to test this sucker. So we've got a couple of ways of doing this. Now remember that if alpha isn't stated, then you're going to assume that alpha is 0.05. Generally speaking, this is the assumed amount for alpha. Okay, so let's get down to brass tacks. How do we test this thing? I'm going to show you the quick calculator way of doing this, and that's by performing a z-test. To perform a z-test, you hit stat, cursor over to calc, cursor over to test, and the very first option is z-test. All right, we're using stats, not data, so we're going to keep stats. And actually, let me see something. We can do a z-test, but let's see if they have. There we go. Well, no, I think they have a proportion. There it is. One proportion z-test. That is what we want to use. So the fifth option. There we go. I like that. So one proportion z-test. So a one proportion z-test, we need to identify p naught, which p naught is notation that I don't typically use, but that is supposed to be this guy. Our population proportion is p naught. So in order to use the one prop z-test, we need to identify p naught. So that's 0.733. We need to know how many people in a sample covered their mouth when sneezing, out of how many, which is 100. And what is the test? We're testing not equals to. Okay, so with all that selected, we hit calculate, and it spits out some values for us. So I'm going to show you how to, first I show you how to pull this test up. And now I'm going to show you how to use the various information here to determine the result of our hypothesis test. Okay, so here in the output, we have a z value and a p value. Those are really the two things that we want to know. What is the z and what is the p? So we got a z value of 1.0624. So that is going to be the critical value. Z critical is equal to 1.0, or sorry, not the critical value. This is the test statistic. 1.0. This is the test statistic. So I'll just put the z. 1.0624. And then we also got a p value of 0.28805. 0.28805. All right. So I wrote them down like this because really we can use these to perform the test two different ways. Your book calls it the classical way and the p-value approach. So the classical approach is to find the critical value and compare this Z value to that critical value. Remembering that we are ultimately doing a two-tailed test, so we have to be careful about what that means. We need to figure out Z of alpha over 2, which for us we'll get by using the inverse norm function and inputting 1 minus alpha over 2. So in other words, our alpha is 0.05, and then that'll get divided by 2. So we'll punch that into the calculator. Second vars, inverse norm, 1 minus 0.05 divided by 2. And we get a critical value of 1.95, call it 1.96. And these critical values are actually always the same for specific alpha values. Okay, so with the critical value of 1.96 and the test statistic of 1.0624, what's the deal? Do we reject or fail to reject? Well, with a two-tailed test, we see that our Z is less than Z alpha over 2. So that means it falls within the fail to reject region. So that implies fail to reject HO. Okay. If we did it by the p-value approach, we'd use the old if p is low, reject the HO approach. So we compare p to alpha, and since alpha is 0.05, we see in fact that p is greater than alpha. So that implies, again, fail to reject HO. So no matter whether we use the classical approach or the p-value approach, we get the same conclusion, or I should say the same result of the test, which is we fail to reject the null hypothesis. Now we have to be able to come up with a conclusion. In order to come up with a conclusion, we're going to use the flowchart. You've seen me use this a number of times. Somehow, no matter what, whenever I'm selecting these problems, it seems to be that always the claim is H1, not H0. That's not always the case, but it seems to always be the case when I'm choosing problems. I don't know why. So first, you identify who's the claim. Is it HO or H1? Our claim is H1. Then we ask, do we reject or fail to reject the null hypothesis? We fail to reject the null hypothesis. So if we fail to reject the null hypothesis, then we go down to this branch. And here, I'm going to have to do a little foldy fold so I can zoom in on this. We did the fail to reject branch. And so our conclusion is there is not sufficient sample evidence to support the claim that blank, right? There's not sufficient evidence to support our claim. Our claim was that P naught is not equal to 0.733. So we're failing to reject HO, which means we do not have enough evidence to support our claim. So when we write our conclusion, we'd say they're using the same exact words as on the flowchart. There is not sufficient sample evidence to support the claim that P naught is not equal to 0.733. And that is the conclusion of our test. Okay, so just to recap. We read the problem, we identified our null hypothesis and our alternative hypothesis. We verified then that our p hat, our sample proportion, is approximately normally distributed by checking this condition. Once we know that, then we can use a z-test to verify or to test the hypothesis. Now, we actually used a one prop z-test, and we got to that by going, hitting the stat button, cursoring over to tests, the third menu, and then going down to number 5, and that was one prop z-test. We then inputted all the stats that we had for our z-test, and that spit out a test statistic value and a p-value. You can use either of those values to come to find the result of your test. So if we do the z-test, if we do the classical approach, then we compare the z to the z alpha over 2 value, which we found by using the inverse norm function. And for a two-tailed test, which this is, we see that the z is falling within the fail to reject region. So it's less than the z alpha over 2. Or we could look at our p-value, compare it to the alpha value. And if p is low, we reject the HO. Well, p was not low. P was greater than alpha. So we failed to reject the HO. We then use our flowchart to formulate and word our conclusion following the flowchart. Then all you have to do is write down the exact words that are on the flowchart and substitute in whatever the actual claim was in your problem. Boom. There you go. I don't know how much easier I can make it. Hypothesis testing for population proportion. All right, let's look at one more problem. This is number 20 from the chapter 10 review exercises. This problem says the mean number of hours spent eating and drinking is 1.22 hours. A p-value of 0.0329 is obtained from a sample of 50. They ask us to state the null hypothesis and the alternate hypothesis and use the p-value to test the hypothesis that people spend less than 1.22 hours eating and drinking. Okay. So let's do it. Hold on. All right, first, we need to identify HO and H1. Now, we can see clearly that we're not dealing with a sample proportion, but with a sample mean. We have a mean number of hours. So for us, HO will be mu naught equals 1.22. And our alternate hypothesis, well, that comes from what the claim is, or what we're asked to be testing. So we want to test the idea that people spend less than 1.22. So that's their claim. So we're actually looking at an alternate hypothesis that's less than. Remember that we could also say mu naught is greater than or equal to 1.22. That would also be a valid null hypothesis for this particular left-tailed test. Okay. Yet again, as I said before, for whatever reason, it always seems that the claim is the alternate hypothesis. It doesn't always have to be. You have to read the problems closely. It just, for whatever reason, whenever I choose them, that seems to be the case. So that's our claim. All right, so now we know our claim, and they've already told us a p-value. They've already told us a p-value. So what do we do? Well, before we can do anything, we need to be careful here, right? Because in order for us to conduct one of these tests, we know that that when we're dealing with the mean, if the standard deviation is unknown, which it often is, then we have to use a t-test to do it. But what's fortunate for us in this problem is that we don't really have to navigate that because they've just handed us a p-value to use. So the only thing that we need to be careful about is making sure that we have a sufficiently large sample size to conduct the test. So we know that the sample size must be greater than or equal to 30. And we know that our sample size is 50. So we're good. Okay. So once we know that, we're good. So now we can just use the old mnemonic. If P is low, reject the HO. What is P and what is alpha? Well, again, they haven't stated alpha, so we'll assume alpha is 0.05. They've told us a p-value, so we compare P to alpha. And what do we find? P is less than alpha. So what does that mean? That means reject the null hypothesis. All right, reject the null hypothesis. Great. What's our conclusion? We use the flowchart. I've shown you how to use it any number of times now. And you'd see that the proper conclusion is that the sample data supports the claim. That mu naught is less than 1.22. Okay, so that one was easy. When they hand you a p-value, there's a lot less work to be done because we don't have to figure out what that p-value is. So I wanted to make sure that I went over the p-value a little bit more. I did touch on it in one of the lectures, but it comes up a lot in the homework and etc. And I just wanted to make sure that everyone was clear on how to use that p-value to generate conclusions for hypothesis tests. So we saw that in two different ways, both for the mean and for the proportion. Okay, so I'll do some more review in the next lecture. It'll be more from chapter 9, and I'll also look through chapter 10 to see if there's anything else that I want to throw in there to help you guys out. There's of course all the other lectures and homeworks and etc. So you should be good to go. I'll again give you more information about the final exam once that's been figured out. Y'all have a good one.